Conservation law, when we're looking at interactions at a quark or lepton level, is mass and energy. Okay, so the basic law is, as we know from all conservation laws, the total mass and therefore energy of the parents must be greater than the combined mass of the daughters. We know that in an interaction, energy is released, and therefore what we expect is the mass to go down a little bit. Okay, so if we're looking at, for example, our lambda becoming a proton plus a antipion, then it must be the case that the mass of the parent, and that's the lambda, must be greater than the combined mass of those two particles. If we look at our tables on the right hand side, you can see quite clearly that we've got a mass of 1,116 mega electron volts per c squared, becoming 938. I've ignored the decimal place here, and a 140. If I add those two together, I get a 1078, assuming my math is correct. And so that clearly shows that the mass of the parents is slightly greater than the daughters. Now, don't expect this to be much of a difference. However, it must be a little bit just to imply that energy is released during this process. Let's look at the same for perhaps a more familiar decay, which is, a familiar interaction, I should say, which is our neutron decaying to become a proton plus an electron and an electron antineutrino. And again, I've included the data here. You can see, therefore, on the left-hand side, we've got our mass of our parent, which is 939.6 mega electron volts over c squared, becoming a 938.3 plus a 0.5, I've ignored the 1, and plus a 0, I really should have included that there as well, and that comes to 938.8. So you can see there that the mass of the parents is slightly greater than the daughter. Okay, so if this happens in your decay, then these are energetically, or you could say massively possible, and therefore they are allowed according to this conservation law. So that's the first thing that we look for in an interaction.